That so that everyone understands. There is also Julien, and he's a PhD student of our team. He's currently in his office, and he's the streaming guy. He's the one taking the stream from Zoom and piping that into YouTube.
Bonjour.
Okay.
Can we start?
Yes.
Okay, so thank you everybody for being here. I am Julien I will chair this defense. And to start, I want to just briefly introduce the committee. So let me just mention your names. So Dominique Attali from INPG and Grenoble. She is one of the two reviewers. Yusu Wang, professor from University of California in San Diego. She is the other reviewer. Who is a professor in Purdue University. Hi, Kamal. Gaël Genbo from INRIA. And Guillaume Rondon from Dassault Systèmes. And next persons are the advisors of the thesis. So David Cohensteiner from here, Florent Lafarge, Pierre Allier, and André Liotier from Dassault Systèmes. Okay, so thank you for coming, and Julien, it's your turn, so please.
Thank you, everyone. Good afternoon, good morning to those joining remotely. So I'd like to start by thanking the committee members for accepting to participate in this PhD defense, which is entitled Planimetric Simplification and Lexicographic Optimal Chains for 3D Urban Scene Reconstruction. So here's an outline of this talk. I'll start by introducing the subject of 3D urban reconstruction and show why we are interested in reconstructing 3D models. We'll then see a first approach, which is looking at parsimonious representation. And in this work, we'll be focusing on simplifying 2D partitions. Then a second approach that will acquire dense representation, and we'll be interested in lexicographic optimality on sublicial chains. And finally, I'll conclude and give a few perspectives to this work. So first, why are we interested? So what are the different kind of representation for urban scenes? So historically, and still the most useful representation are in the form of two-dimensional data, so such as vectorized maps as shown here. However, there are a lot of other kinds of representations, especially 3D ones. And many of you are probably aware of the Google Maps live services, which offer to explore cities around the world in 3D. In a more professional approach, people who are interested in urban planning usually use what we call geographic information systems, which are databases that contain various sources of information and which combined can be used to understand better complex phenomena at play in cities. And in these systems, buildings are often represented as level of details. So at the coarsest level, we simply have the footprint of the building. And when we go towards higher levels of details, we add geometric information as well as semantic. And finally, people that are working in construction and civil engineering will be familiar with the building information model, or BIM, which is a 3D representation, a very complex one, which combines all the information that are needed for construction And yeah, so in this thesis, we'll be interested in two approaches, two different representations. The LOT2 one that will be useful for geographic information systems, and acquiring a dense representations such as the one from Google Maps. So why do we need 3D models? Well, I give here a few examples. In the domain of simulation, wind or sun exposure simulations are often done on log models from geographic information systems, and require therefore parsimonious representation, three-dimensional representations. The kind of simulation, for instance, could be 5G connectivity, where here the high frequency waves requires very precise geometry, and therefore we often use dense representation. The log geometry is not enough. Another domain, which is where these 3D models are interesting, is change tracking. And here we can mention verifying construction permits. So for instance, if you have a database with the construction permits and you have acquired a 3D model of the city, you can compare both databases to see if each building has the right construction permits. And another application in change tracking is to inspect a construction site at a certain time and verify that there are no defects in the construction in the build. So now that we've seen how we can use those 3D models, let's investigate the different ways we can acquire large urban scenes. There are mainly two technologies that we are interested in. The first is a LiDAR technology. The second is imagery. With LiDAR technology, we use a laser to measure precisely the distance from an emitter to the surface of the Earth. And if we can correctly position the device that is capturing, that is emitting the laser beam, we can create a 3D point cloud representing the surface of the Earth. Another approach is to take images, and in the process of photogrammetry, we position those images in 3D space. And using those positioning in space, we can estimate the depth of each pixel of the image, and therefore create as well a point cloud that represents the scene. So both types of acquisition have different characteristics. Usually LiDAR are very precise, but lack information on facades. Whereas with photogrammetry, we don't have this problem. We often have less of this problem on facades. However, we might have noisy point clouds. So let's give the scope of interest of this work. So we've taken as inputs these set of points from both methods, and we want to develop semi-automatic methods of reconstruction. So by semi-automatic, we mean that we allow a few user interactions during the process, but we don't want to design each building individually. And the first approach looks at parsimonious representation, especially we'll be targeting LOT2 reconstruction. This approach will be limited to buildings only, and the focus will be put on simplicity and regularity. And the second approach, we're going to construct a triangular mesh. Here, we're not restricted to only building. We can reconstruct larger urban scenes. And the focus will be to get a method that is as generic and efficient as possible. So let's start by looking at the parsimonious representations. So the general idea of, so again, we're starting by, as inputs, we take point clouds of built structures. And as I said before, as output, we want LOT2 representations, which looks like something on the right. Mathematically, the LOT2 representation can be seen as the support of a piecewise linear 2D function. And therefore, a lot of approaches have reduced the problem of reconstruction to a 2D partitioning problem. And you see that if we can reconstruct correctly a two-dimensional partition of the space, by lifting each cells of this partition, we can construct a 3D model that can be used for lot 2 representations. So with this idea, I'll quickly summarize a reconstruction pipeline we've used. So in the first step, from this set of points, we use the nearest neighbor and a region growing approach to detect planes in the set of points. Because we're using a nearest neighbor, we are able to have an adjacency information between planar primitives, and therefore we can compute intersection lines of adjacent planes. And we can restrict those intersection lines around the set of points to get 3D segments, which we then project into D. Once we have all those two-dimensional segments, we are interested in getting a two-dimensional partition. So one idea could be to compute all the intersection of the line supported by the 2D segments. However, this would lead to way too many intersections. So instead, we use a kinetic approach, which is basically a set of rules that define which segments should be extended and which should be stopped. And this gives us a 2D partition that is a lot sparser than if we were to calculate all the intersections. Note that in this representation, we have a lot of collinear segments. And this will be important to the method we'll describe. And finally, once we have this 2D partition, we want to lift this back into a 3-dimensional model. And there we use a Markov random field formulation, which, as its fidelity, will try to be as close as possible to the 3D point cloud. And we'll have a regularity term that avoids having too many height jumps between neighboring cells. Once we use this reconstruction pipeline on some real data, what we observe is that the 2D partitions are very complex. And especially we have a lot of very small edges, and the angles are concentrated around 90 degrees, but are not exactly 90 degrees. And with this observation, when we lift these two-dimensional partitions in 3D, we see a few incoherences that appear in the 3D model, as well as some misalignments between facades of buildings. So our interest is we propose to simplify this two-dimensional partition, and especially we want to use a continuous optimization that will both simplify and regularize those two-dimensional partitions. The first question we need to answer is how do we represent those two-dimensional partitions? So in the first approach, we try to use a point representation where we give explicit coordinates x, y to each point, and segments are defined implicitly at each segment will be supported by 2 points of the partition. Using this, again, because of how we constructed our two-dimensional partition, we have a lot of collinearities between segments, and those we want to preserve, which means that if we have an optimization scheme, we need to optimize under constraints of keeping those collinearities. And I won't enter into the details of how we formulated this first approach, because there's essentially a big problem with it. The fact that if we try to essentially collapse small edges, such as this one, such as the image on the right, the objective will tend to create very close points that are very close to each other, and this will actually make the collinearity constraint unstable. So our objective of simplification goes against the numerical stability of the system. So instead, we propose to use a line representation where we give explicit coordinates to lines, and points are defined implicitly at the intersection of lines. And here we have baked in the fact that the collinearity are preserved from the structure. So the explicit coordinates we give to lines are in homogeneous coordinates, a three-dimensional homogeneous coordinates ABC from the line equation. And we use a Euclidean normalization, a squared equals b squared. So our line coordinates are on the cylinder, or on a cylinder at a distance 1 from the axis OC. And we formulate our energy as a trade-off between fidelity and regularity. So let's describe those terms. The first term of fidelity, we want the optimized partition to be as close as possible to the initial partition. However, we have one problem, which is that there is no natural distance between lines. So, which means that there is no distance between lines that is invariant under Euclidean isometries. To circumvent this issue, we propose to construct a fidelity term that is based on the initial segments that are associated to each line in the partition. And so we write a symmetric matrix which computes for each Euclidean normalized line the square distance between the endpoints of the segment that is associated with the line. And the fidelity term will be the sum of those quadratic forms. For the regularity terms, we have two. The first one, we want to simulate an edge collapse in the partition. And for that, we use a term based on triplets of lines, which is the absolute value of the determinant of the 3 line coordinates. And because we've used Euclidean normalization, we have a very nice expression of this term, which is the distance between the 2 intersection points between the 3 lines times the sinus of the angles between the lines, which means this term will be equal to 0 either when the 2 points are the same, which means we've made an edge collapse, or the sinus of the angle is 0, which means 2 lines are identical. And in this term, we add a threshold because we only want to consider small segments. We don't want to consider very large segments. Therefore, we use this thresholding value. And for our orthogonality term, we use the inner product on the 2 first coordinates of the lines, which in Euclidean normalized coordinates is equal to the angle between the lines. And again, we threshold this value because we only want to consider angles that are close to orthogonality. So we want to optimize this objective function using a gradient descent approach. However, there's a few subtleties to this method. The fact that we're using lines means that, so in the Euclidean case, the gradient is equal to the derivative, the transpose of the derivative of the function. In our case, because we're using our parameters are the line coordinates, we are more in a Riemannian manifold, and therefore the relation between the gradient and the derivative is linked by the tensor metric. So So what we do is we explicit the tangent space of the manifold of the, so recall that the manifold we're considering is the cylinder at a distance 1 of the axis OC. And we start by writing we parameterize the tangent space of this manifold. And so we write it as the matrix UI times the two-dimensional parameter space. In this tangent space, the matrix MI, which we've defined for the fidelity term of our optimization, we see that it is a non-degenerate quadratic form. And therefore, we can consider it as a Riemannian metric for our problem. So I won't go into the details of the computation, but we can then write the gradient in homogeneous coordinates as follows, as the Riemannian metric in the tangent space -1 and multiplied by the derivative in the tangent space, and we project back those value into the homogeneous coordinates by applying the matrix UI. Finally, so just as in gradient descent, we update our coordinates, our old coordinates, by decreasing of a step times the gradient. And because we want to stay on the manifold of Euclidean normalized line, we add a normalization to these coordinates. During the continuous optimization, we add discrete operations, which actually simplify the combinatorial nature of the 2D partition. So those discrete operations, we can determine when they happen, when we saw that there were two possibilities when the absolute value of the determinant of 3 line equals 0. Either we have two equal lines or lines meet at the same point. So in our representation, we're able to merge lines. However, we need to take special care because in the optimization, we can never have that this term is exactly equal to 0. So we have to see what happens when we use a threshold instead. But when we merge those lines, we also merge the quadratic form associated to these lines. And this is, as you can see on the right, this is very natural. If we have a line after merge, we want the fidelity of this line to be associated to the two segments that originated before the merge. And this is similar in the approach to the quadratic error metric. So here's a few iterations of what happens during the simplification. So we can see that we correctly simplify the partition and also add some artifact, also preserve the collinearities and regularize the partition. We've compared these results with other simplification methods. What is interesting to see is, so those methods do not take into account the regularity of the output mesh. So what is interesting to see is that our approach is comparing our reconstruction pipeline without simplification and with simplification, and we see that we decrease the error and complexity of the generated models by using this simplicity, both in the LiDAR and photogrammetry case. Here's another few results on some buildings and on a slightly larger scale. Finally, there's a few limitations to this approach. First one is in the nature of the model we're trying to reconstruct. So if we have a building that has a lot of openings, the reconstruction will not be accurate. A second problem that is more troublesome is that there are sometimes differences between the 2D and 3D regularity. So here we see the 2D partitions that are we see that we correctly simplify the 2D partition. However, when we see the 3D result, we observe that we've changed completely the nature of the facade. I'll now look at the second approach we've considered, so using dense representation for lexicographic, using lexicographic optimal shapes. So here I'll start by giving an intuition of the problem. So let's imagine we have a set of points in 2D, and in blue we have inliers, so that are close to the surface we're trying to reconstruct, and in crosses we have outliers which are far from the surface, from the path we're trying to reconstruct. Let's assume also we know the endpoints of the curve that we're trying to reconstruct. So in this setting, what is very natural is to consider a shortest path problem. So we first start by, so let's consider that we have the dense graph, which means we have an edge between any 2 points of this set of points. And we start by looking at the shortest path in this graph. So the shortest path is not really what we're looking for. It doesn't go through the inliers. It goes far. It doesn't follow the shape that we're expecting, and it uses a very long edge. So what can we do to remedy that? Well, we can consider, instead of taking the sum of the length, we can consider the sum of the squared length. And in this case, we get a path that is slightly better. We go through a few more inliers to start in the end here, but we go through outliers and we don't reconstruct the whole shape. But following the same idea, we can use an exponent, a larger exponent. And for exponent 8, for instance, here, we get this curve, this path, that is a lot closer to what we're looking for. It goes through, it doesn't go through all inlier points, but that's okay. But it does follow the right shape of the set of points, and it avoids outliers. So what have we constructed by using these larger exponents? Well, let's first assume that we have a total order on the edges, which are based on their length. So we can order from the edges from E1 to En. We have this property that for an exponent large enough, and for any edge EI, the lengths of this edge to the power of P will be greater than the sum of the lengths of all the edges that are smaller to this one, the power of P. Which means that if we need to compare two paths, P1 and P2, what we can do is simply write those paths we can write the edges on this path in decreasing order and compare the largest edge. Start by comparing the largest edge. If one of these edges is larger than the other, then we know that, for instance, P1 is larger than P1 prime. We know that P1 will be larger than the path P2. And if we have an equality on those edges, because we've used a total order, we know those edges are the same, and we continue on this. We continue on the second edge, our comparison. So what I'm describing here is exactly a lexicographic order where the edges have been sorted in decreasing order. So let's see how we can generalize this approach, especially in the context of simplicial homology. So we consider that K is a simplicial complex, and we'll have a field F. And Ck K of F will denote the vector space of K chains. We'll assume we have a total order on K simplices. We'll see how we can generalize this from the total order on edges to triangles. And the lexicographic order, we can define a lexicographic order on chains where gamma 1 will be smaller than gamma 2 if either their supports are equal or the maximum simplex in the symmetric difference of the supports is in the second chain. So we see that this is a pre-order because when we have an equality with this lexicographic order, we can only say that the chains have equal supports. However, when the field we're considering are integer modulo 2, then we have a total order. So let's immediately look at how we can generalize the total order on two simplices. So recall that for one simplices, for edges, we used simply the length. For two simplices, the order is slightly more complex. So we compare two triangles by first comparing the radius of the smallest enclosing ball of the simplices. And in case of equality, we have the inverse relation on the radius of the circumscribed sphere. So why do we need those two quantities? Well, generically, it is possible for two triangles to share their longest edge, and therefore have the same bounding radius. But we can say that generically, the two triangles cannot have the same radius for their circumscribed circle. In fact, we justify this order from the fact that if we take a two-dimensional set of points P, and we consider gamma P to be the boundary of the convex hull of this set of points, we have a theorem that we show the theorem that minimizing in a set of chain in the full complex, which means all the complex you can possibly create on this set of points P. Minimizing the chain that is bounded by beta P, the support of this chain corresponds to the two simplices of the delineated triangulation, which means we can characterize 2D delineated triangulation using a lexicographic optimal using this total order on two simplices. And in fact, we can generalize a total order for simplices in any dimension. And using this generalization, we can also characterize regular triangulation as lexicographic optimal chains. Now let's see the different problems we are interested in terms of simplicial homology. The first one is finding the optimal homologous chain, the optimal chain homologous to a given chain alpha. So if we have this chain alpha here, we're going to be looking for the chain alpha min, which is homologous, which means the difference between the two chains is a boundary. Here shown, highlighted it in dark. The second problem is finding the optimal chain that is bounded by given boundary beta. So in 2D, if we give 2 points here beta, we'll be looking for the one chain gamma min that is bounded by those 2 points. So this is exactly the same problem as what we saw in the intuition, however formulated in a simplicial mode. So when considering those problems with integer modulo 2, those two problems are NP hard for general simplicial complexes when considering L1 minimization. However, with lexicographic optimality, we can derive polynomial time algorithms. And I won't enter into the details, but the key idea for those algorithms is in the way we represent the boundary matrix. So the boundary matrix, the columns of the boundary matrix are the k+1 simplices written in the basis of the k simplices. And what we do is we order the rows of the column, the rows of this matrix using our total order on k simplices. Once we have this boundary matrix, we essentially use matrix reduction algorithms that are normally used for computing persistent homology. And those algorithms have cubic complexity on the size of the complex. Once we have these reduced matrices, boundary matrices, we have a few nice properties about them that allows us to solve those two problems. But essentially, the complexity of solving those are bounded by this complexity of this matrix reduction algorithm. I want to spend a little bit more time on the efficient versions that we derive in codimension 1. So here, we assume that the simplicial complex we're looking at is a D pseudo-manifold, and we're going to be looking at D-1 chains. So in 3D, we'll be essentially constructing the Delaunay triangulation, and we'll be optimizing for 2 chains. So there's 2 versions that we're going to be looking at. The first is a closed surface reconstruction algorithm, where we are going to give as input 2. So in 3D, we're going to give 2 tetrahedra and find the optimal, the lexicographic optimal 2 chain that is homologous to the boundary of one of those tetrahedron in the complex where we've removed those 2 simplices. And the open surface reconstruction, we're going to give as input the boundary here in purple, and we're going to find the lexicographic optimal chain that is bounded by this boundary. So for the first algorithm, so if we illustrate this problem in 2D, we have again those 2 simplices. So here in 2D triangles, in a complex where we've removed those triangles, we're going to find the one chain here, one cycle gamma min that is homologous to the boundary of tau 1. Because we are in a pseudo manifold, we can define the dual graph of this complex, and this allows us to formulate a dual problem, which is that we're going to look at the set gamma min that is lexicographic minimal and separates the dual vertices tau 1 and tau 2. So how do we verify this property of separation in this dual graph? We use a classic structure, the disjoint set structure. So we can see it as a tree representing each set. And if we want to verify that 2 elements are in the same set, we call the find set operation. So in this example, if we call find set 3, in the structure, we get the root element of the set 5. And for any other element in the same set, for instance, 8, we also get the same value, which means we can verify very efficiently that the 2 elements are in the same set. And the other operation that we allow is to link sets. So essentially, merging 2 sets. And this adds an edge in the data structure. So this has a very good complexity, alpha n for those operations, where alpha is the inverse Ackermann function, so a very slow growing function. So here's the algorithm we use for the closed surface reconstruction. So at the start, we have all the vertices of the dual graph in separate sets. We then iterate on the edges of the dual graph, which in the primal graph in 3D will be the triangles. So we'll have, when we iterate in decreasing order, we have the decreasing order on the using the total order on the 2 simplices. We call the find set. So for each edge, we call the find set operation on each vertices to check their connected components. And what we want is to the property we want to verify is that the sets the sets containing TOE1 and the sets containing TOE2 are separate. So in this case, for this edge, this doesn't connect TOE1 and TOE2, so we can add it to the disjoint set structure. And a few iterations later in the algorithm, we might consider this edge here, where if we add this edge, we essentially connect the connected component of TOE1 and TOE2. So in this case, we're going to keep this edge in our solution set. So running this algorithm is efficient in n alpha n, and as a precondition, we need to sort the dual edges to perform this iteration in decreasing order, which is an n log n operation. So here's a result. Here's one of the first results we had with the screen doesn't. So I'll describe the image. On the left, we have a set of points that contains a lot of noise. Here we have a mine where we have people and cables. And one nice thing with the lexicographic optimality formulation is that we avoid a lot of noise. And here we only get the walls of the mine gallery. Let's now look at the second efficient version for open surface reconstruction. So as input, we have a set of points as well as the boundary here shown in purple. So this is a two-step algorithm. We start by computing a representative chain, which is basically any two chain that has as its boundary the cycle we are looking for. And using this representative chain, we now look for the lexicographic optimal chain homologous to this representative chain. So I'll go quickly over the first step. Here we have a solution in the Delaunay triangulation, where basically we recursively replace the highest point of the boundary by a path in the lower link. And every time we do this, we record the triangles that are generated at this step. After we've iterated, and this algorithm terminates when the boundary is empty, and then we know that we have a surface that is bounded by the initial cycle A. We can do this in n log n complexity. The second part, finding the optimal homologous chain to the representative chain, this is very similar to the first algorithm, except we need a little bit more, a few more duality properties. So first we need an intersection product between two chains of the complex and one chain of the dual complex. So this intersection product is the can be seen as the inner product of the coefficients of the chains on the K-synthesis of the complex. Using this intersection product, we have a Leschetz duality, which can be illustrated here. If we have gamma, if gamma is a two-cycle, and we have any beta one boundary of the dual graph, the intersection product, which which can be seen as the number of times we enter the two-cycle and go out, should be 0. And we have, and what is useful in our problem is the part where we have a delta, which is a two-boundary of the complex, and we take any one cycle of the dual graph, and we look at the intersection, and this intersection should be 0, which allows us to reformulate the problem of finding gamma that is homologous to gamma 0. This normally is, this is by definition that the difference should be a two-boundary of the complex, and using this duality, we can show it is equivalent to verifying that for all one cycles of the dual graph, the intersection product is 0. So this is what we're going to be trying to verify. We need to have a way of finding all the one cycles of the dual graph, and we need to verify that the intersection product is 0. So to do that, we modify our disjoint set structure by adding values between the nodes, between the parent nodes. So the modified versions of the find set returns 2 values. So if we call find set 3, just as before, we get the roots of the set, so 5 here, but we also get the sum of the values along the path. So here, 1 minus 1 plus 1 equals 1. And the link set operation is similar to before. However, we add a value to the edge that we're adding to the disjoint set structure. What this allows us to do is, again, what we're trying to verify is that for any one cycle of the disjoint set, we have that the intersection product is empty. In our algorithm, we have 2 invariants that we keep. We say that we have that for any edge in the augmented disjoint set structure, the solution, the coefficient of the solution on this edge of the augmented disjoint set structure is 0. The second invariant is that for any edge in this augmented disjoint set structure, the value that we store is the intersection product between gamma 0 and E. And when we want to verify, for instance, in the algorithm, when we will add, when we will consider an edge from 6 to 4, for instance, we have to verify, we call the find set operations on each element. And using the first value, we know that we are in the same set because both return 5. So this means we know we have created a new cycle in the disjoint set in the dual graph, and therefore we need to verify that this intersection product. Thanks to the 2 invariants here, the only unknown of this equation, let's say, is the value that we add on this edge to gamma min. And we can show that this value of the solution on this edge is exactly the intersection product of gamma 0 with this cycle alpha, equal alpha, in the augmented disjoint set structure. And we can compute those with the value returned from the find set operations. So this slight augmentation of the disjoint set structure allows us to verify those intersection products between one cycles of the dual graph and the one boundary where. Here's a few applications of this open surface reconstruction. So on the left, you can see a set of points where we've drawn a very large one cycle around it. And after reconstruction, what we can see is that we can deal with large amounts of points in the millions. And in terms of performance, what takes the longest is computing the Delaunay triangulation. The final application we've looked at concerning those lexicographic optimal chains, we've considered the application MLEX, which takes for any K chain returns the optimal homologous chain, the optimal chain homologous to gamma. This application is linear, which means we can define the vector space of lexicographic optimal chains. So ZK min will be defined as the image of MLEX of the cycles by the application MLEX. And this, from the linearity of MLEX, is isomorphic to the homology groups, the K homology groups of the relative complex in this case, which is a very nice property, which means that for any homology group, we have a unique lexicographic optimal chain associated with this homology group. And so what we try to do is to define a basis for this space ZK-min, and we do as follows. Recursively, we look at the optimal lexicographic chain, which is not in the span of previous elements of the basis, and we add this criteria on. So crit of gamma is the maximal support in the support of the chain, and we add this condition to create a canonical basis. So the first element of this basis will be the smallest non-zero chain in ZK-min, and for instance, the second will be the one that is the smallest that is not in the span of the first. This allows to create a nice application for open surface reconstruction, where the boundary would be difficult to define. So in this example, we use the Delaunay complex of a set of points, and we use a sharp edge detection. In practice, we use a Voronoi covariance measure to tag a set of points in the point cloud as being sharp. So once we create from this set of points, once we create the subcomplex B, we can compute a cycle basis of this subcomplex, which kind of give a wireframe view of the scene we're trying to reconstruct. From those one cycles, we can then compute a critical basis, which gives a sort of patchwork of two chains which reconstruct the scene. And one interesting property of this is that if we remove the first few chains of this critical basis, which correspond to the largest element, the largest two chains in the lexicographic sense, we get the kind of the natural holes that we see here behind the cars. We have a few holes in the set of points, and those correspond to the largest element of the critical. So let me conclude on this work. So we first saw how we can reconstruct a parsimonious representation, especially targeting log2 representations for geographic information systems. Our focus was mainly on simplifying 2D partitions using a continuous scheme. The particularity was that we used line movements, and therefore we had to the usual gradient descent algorithm was slightly modified from the definition of the Riemannian metric associated with each line. A few continuation of this work would be first to improve the fidelity to 3D data. We saw that one large problem we had was that sometimes the 2D simplification did not correlate well with the 3D simplification task. And secondly, we could imagine generalizing this idea to three-dimensional polyhedral arrangements. For the second approach we've considered, so we've defined a total order on simplices, which is linked to a characterization of Delaunay or regular triangulations. We describe general algorithms that use matrix reduction, are usually used for persistent homology to solve optimal homologous chain problems. And we described efficient versions both for closed surface and open surface reconstruction, which were useful in the case of urban reconstruction. And finally, we defined a critical basis and showed how we can use a sharp edge detection in application where defining a boundary would be difficult. and yeah. So there's a few continuation to this work. But first, we think we can generalize the algorithm we presented to persistent versions. We could also, one very key improvement of this method would be to automatically be able to give the interior and exterior detection, which are required for the closed surface reconstruction. We need to give an information of interior and exterior. And finally, we could look at how weighted points, because we have also an order on weighted points, we could see how using a regular triangulation could help the reconstruction test. So thank you for your attention, and I'll answer any questions you have.
Thank you. So now we move to the second part of the defense and the questions. So we will start with the two reviewers, and you, Sue, maybe you can start commenting and asking questions.
Sure, thank you for the very nice presentation. So let's see. Maybe first a more high-level question. So for the first part, this generating this LOD2 level of this urban scene. I understand that in this case, you assume that you essentially are generating a piecewise linear function defined on R2. Now, I'm curious whether you tried on data where the input point clouds actually violated that condition, and how does your algorithm perform in that case, even though that's not designed to handle that case?
Yeah, so there's this example, maybe I can show it on the slides, where if we use this algorithm on a structure that cannot be this example here on the top. I'm sorry, on our side we don't see the image. In the top example here, basically this cannot be correctly represented as a two-dimensional function, the support of a two-dimensional function, because there's a ground and then there's the building. And so, yeah, in this case, the method doesn't accurately reconstruct the scene, indeed. Yeah.
Do you have some thoughts on how to tackle such cases?
So I think if we wanted to deal with those kinds of buildings, we would have to either go further in the level of details. So, for instance, if we first detected that there were some openings in this building, we could deal more efficiently with those buildings. Yeah, this definitely the fact this could not be correctly represented in the lot 2 model, so we would have to go further, lot 3 or. Yeah.
Thanks. So for the second part of the work, I see that so some of the results, I mean, the property of this optimal lexicographical ordered optimal basis connects to the Delaunay triangulation. I'm wondering that for the final result, including a reconstruction, how much of it really relies on that the input has to be a Delaunay triangulation? It seems that most of them, you don't need the Delaunay triangulation, no?
Not sure, I didn't quite hear the end of the question. Can you?
Right. So, for example, in your applications where you reconstruct the surface or the open surface, you start with the Delaunay triangulation, yes, right, of the points.
Yes.
Especially in the case when you are reconstructing a surface without a boundary case. Do you really need Delaunay triangulation?
No, yeah, that's an interesting point. Yeah, we could use a smaller complex. This would be better if we could find a complex that was smaller. We would have a more efficient method for sure. But because our algorithms use the fact we need a pseudo-manifold, the Delaunay triangulation is still one very efficient complex that we can compute to get this pseudo-manifold. So yeah, in theory, in theory we could other complexes, but we would then have to use the cubic time algorithms to do that.
I was also thinking, I mean, let's say that you start with some triangulation, and right now you take these two simplices, I mean, tau 1 and tau 2, right? And then you find the optimal cycle that's homologous to 1, say the boundary of tau 1, right? Suppose you already have some total order on the simplicity, which you do. One could run the persistent homology, right? And one can potentially pick a two-dimensional homology class with a large persistence, and then try to find a representative optimal, this Lex optimal representative of that class. Would that be an alternative way? Or, I mean, what is the downside of this approach compared to what you're doing?
Yeah, thinking. Yeah, for sure. I think I think it would be a good idea to indeed run the persistent algorithm, which would probably give us. Trying to think if the class we would get would be actually the one where we want to. That corresponds to the surface we're trying to reconstruct.
Right. So I guess the filtration order do matter, that you really hope that corresponds to some class with large persistence.
Yes.
Right. But this could, I mean, this could resolve the issue that you don't rely on a triangulation of R3. You can have any simplicial complex presumed potentially.
Yes.
As long as the filtration makes sense.
Yeah. So you would you mean having then another total order that was not, especially this one that is linked to the Delaunay triangulation, right? You just used any persistent, yeah.
Use some total order whose persistence is somewhat meaningful.
Yes, this could.
And then, but whose lexical optimal cycle is still meaningful in the sense that to give you the desirable surface.
Yeah.
Right.
I think, yeah, it's an interesting idea. I think it's worth exploring.
And also the reconstructed two cycle, they don't have to be embedded the two manifolds, right? They could have pinches.
No. Yeah, exactly. They can have some non-manifold configuration. Yes, locally. For instance, you could have two, let's say, interior tetrahedra that are touching on one simplex, therefore creating a non-static. Yes. However, yeah, those cases are easy to deal with. We can slightly shrink the surface around those configurations and get something that is embedded.
So more precisely, you're saying that there's a strategy that that can resolve this.
Yes,
was correct.
We are essentially in the first part, we are tagging all our, you can see it as a tagging of all our tetrahedron as inside or outside. And the number of cases we have then is two interior triangles touching on either the vertex or on an edge. And in those cases, we can basically do a kind of ISO cut around those problematic configuration where we add a few points along the edges. Basically, if you have a problem around this edge, you can shrink slightly the interior surface to separate this edge into two edges, and therefore creating a manifold surface.
All right. Thank you. I don't know how it works. Maybe I'll pass for now, and later if it comes back, maybe I'll ask more. Thank you.
Thank you, Yusuf. So move to Dominique Attali.
Yes, can you hear me?
Yes.
Okay. So thanks for the nice presentation. Also, I would like to congratulate you for your work that I find impressive. I would like to go back to the first method for reconstructing LOD representations. And I would like to continue the question that Yuzu asked about the assumption that you make that the roofs are piecewise planar, piecewise linear. And so now imagine that you would like to add the assumption that the roofs may contain some spherical part, some domes, say. You want to reconstruct igloo. Would that be possible to modify your method to take into account this new assumption or this modified assumption?
So I think it depends on whether this affects the 2D partition or not. So we can imagine that the base of the igloo is still using segments, let's say, and then you have in the maybe the way you lift this 2D partition, you could use other primitives such as spherical ones for the igloo, I guess. Or in the initial detection, you could detect other things than simply planes. You could also go for cylinders and some of those things. However, if it's a lot more complicated if it affects the two-dimensional partition. If we're not working with curves, I'm not sure how we can devise a simplification scheme on curves in the 2D space.
Okay, so you think it would be a profound transformation of your algorithm.
Yes.
I have another question regarding this first method. So it seems that the angles that the line are making, a lot of those angles are 45 degrees. And I was wondering if there is a reason for that. Is it just the data that provides this? And is there a way to enforce an angle of 45 degrees between lines? So to add this constraint?
Yes, I think it's the 45 angle degree comes from the fact we project 3D segments in 2D. So when you have, let's say, a four-plane roof, to project the intersection between the four planes in 2D, you will get 45 degree angles between those segments. So let's say in most urban architectures, it's quite common to have those angles of 45, and so I think it's completely possible in our optimization to add a term for 45 degree angles, just as we did for 90 degrees.
Mm-hmm.
I think there's a limitation to that. We could add the other angle constraints to the method.
Okay. So I was very intrigued by the computation of canonical basis at the end of your PhD, at the end of the presentation also. And I was wondering, I'm not sure I see what one would want, what would be the expected result that you would like for an application.
Yes.
So there seems to be a gap between computing this basis, this cycle basis, and also what you would like. Yeah, what would, so can you elaborate on this?
Yes.
Do you think? Yeah.
Sorry, go ahead. Yeah, so I think what we're trying to do in the application is essentially the open surface reconstruction is interesting, but very limiting because defining properly the boundary, the boundaries for this for this set of points is very difficult. So the application would be to have an automatic method to reconstruct, to detect the boundary for this kind of. What we use instead is what we would like is to have a boundary detection. It's not very precise to say boundary in a set of points, but we would like to have the kind of visual boundary, let's say, of the set of points. What we use instead is a sharp edge detection. So the subdivision we have is we have a lot more cycles that's not particularly what we want. And yeah, therefore this creates indeed a gap between the reconstruction that we would want and what we can actually get from critical bases.
So there is still work to do to simplify this basis.
So I think there's maybe two ways we can improve on this. First, we could look at maybe a better detection, which would not simply be a sharp edge, but I don't have really an idea how, but would be closer to the visual boundary of the set of points that we're seeing. Mm-hmm. That would be one way. And the second would be to have a automatic way of merging those critical bases that we have now to actually construct a single two chain that represents the whole scene, instead of having this patchwork of small chains.
Okay, so maybe a last question. Are there other orders that may be interesting to consider on simplices?
I don't know. That's the honest answer. We've tried a few other, such as the area of the triangle, for instance, or we've also tried just using the radius of the bounding as the smallest enclosing wall, and not using the second condition. It also gives some results that are not as nice as this order that is justified geometrically with the Vuillamy triangulation, but we still get interesting results. And the main difference that we see is if we count the number of non-manifold configurations that appear in using other orders, there are a lot more of those non-manifold configurations than when we use this order linked to the Vuillamy triangulation. So there could be other interesting orders, and the order on regular triangulation, which is very similar to this one, but this one is also, of course, interesting.
Interesting. Thank you. I'm done.
Okay, thank you, Dominique. So we will now move to the evaluators. So Tamal, are you here?
Yes.
Okay, so please ask your questions.
Okay. So first of all, I was reading your thesis couple of days. I really enjoyed it. It's a heck of a thesis. I must say that. It's such a nice thesis and such a nice result. Okay, on this, let me ask you a couple of questions. First, when you take the tetrahedra and you constitute this surface through duality and the cut, is this closed surface always genus 0? I'm not sure, but I just want to verify this.
So if we only have one, let's say, interior constraints, the only one tetrahedra, I think we cannot have another, which would be another boundary basically. If we have two parts, so I think it's
So, am I right that you cannot reconstruct surfaces which have non-zero genus?
Actually, I think you can reconstruct. For instance, you can reconstruct a torus if you have only one interior. You will, if it's still sampled correctly, you will get the reconstruction you're expecting. Yeah, I think so you can start to.
I cannot hear you. You can reconstruct torus or
yes.
cannot?
I can reconstruct torus, yes.
Okay. Okay. The other questions I have is actually the critical basis. I was trying to understand it in more details. It's very interesting. So if I understand it correctly, and please correct me if I'm wrong. So first you have to have you call it basis, but what I say that it's a collection of two chains in Z2 mean, which must contain at least an optimal critical basis, because if it does not contain, then you cannot, using the greedy algorithm, you cannot have it. But my question is, how do you get the Z2 mean, a basis of Z2 mean in the first place, having this property?
So can you see the current slide here with the application? Yes. So we have, once we have this Z1 min of B, we can compute, using the first algorithm, we can compute a representative surface for each of these one cycles. So this gives us two chains. Then we can optimize those two chains, which will be elements of Z2 min.
Oh, I see.
So this, in this example, at least, this gives us a basis of Z2 min, but then we have to again optimize it to get the critical basis along those elements.
Mm-hmm. But is it obvious that what you get, the basis of Z2 mean, always will contain an optimal basis?
Will contain the critical basis?
Yes. Is it obvious or it requires a proof?
No, I think it depends on the complex K in B. In our case, we use the donated complex, which is isomorphic to the 3-sphere, and this is what makes it possible to, I think, get a basis of Z2 min.
I see.
If you have another complex, maybe this would not be the case.
Mm-hmm. Okay, thank you for clarifying this. Yes. I have one more question. So have you verified, so this reconstruction method, so we have this other classical method like crust or cocon, or whatever. And given a dense enough sample, these methods are known to reconstruct correctly, means it will produce a manifold no matter. So is it true that this method, if it is dense sample dense enough, then it will always produce a manifold, or it will always reconstruct it correctly?
So yeah, this is a bit outside of the scope of this thesis, but yeah, we have a result that with condition on the reach of the manifold, on the sampling that we use, and and on the complex, the tarameter of a RIPS or Vitteris complex, we can show that it is actually a triangulation of the sampled manifold. Yes. But,
so it will not, and in practice, it does not produce any non-manifold in this case when it is a really dense sample.
Yes, yes. In this very, maybe I think I have a slide for that. So the theoretical guarantees are very strict. So here in the case of a torus here, if it's so maybe on the left we have exactly the condition, let's say of the theorem. When we add a bit of noise, we still have a triangulation. We still have a zero non-manifold configuration, and it's only when we add more noise. So we are very far here from the theoretical guarantees, but here we see the first non-manifold configurations. So it does hold, for a very dense sample.
And suppose you did not start with the Delaunay triangulation. Suppose you took the entire complex, like the full complex, complete complex, and you apply your method, and the reconstructed surface, what you get, do you know, is it always going to be a subcomplex of Delaunay?
Yeah, that's an interesting question. We ask ourselves the same question. I think there could be situations when we would get simplices that are not in the Delaunay triangulation, but this would have to be verified. If we took a complex, the full complex, we might have triangles that are not in the Delaunay triangulation.
Thank you. Again, congratulations. It's a very nice results and very nice thesis. Thank you. I'm done.
Thank you, Tamer. So, Gaël Guimbaud, would you like to ask questions?
Yes, thank you. Thank you, Julien, for these very nice presentations. I think it complements very well your manuscript. It helps, at least it helped me to better understand some high-level ideas of your second contributions. And before asking a few questions, I would also like to congratulate you for this impressive amount of work. And I would also like to emphasize the computational speed of both of your algorithms, which are both very impressively fast, I think. And even so, actually, the execution speed was not really the focus on your thesis. So I will start with the first method. So as you already mentioned, your algorithm to simplify the 2D partitions completely ignores all the information from the initial 3D point cloud. And I'm wondering why you choose to solely work on the 2D partitions, and why it seems to me that a natural approach would have been to try to directly optimize for with respect to the input, to the 3D input. So why have you not considered that? And do you have any idea how to extend your approach to take into account this, the 3D information?
I think for the regularity terms, it made sense to only consider 2D information, because here we're trying to basically do edge collapse regularity in the 2D partition. But I agree that it might seem more natural use immediately the 3D data to construct a fidelity term. I think the reason we didn't use the 3D data is because we didn't find any good optimization techniques for describing the fidelity using the three-dimensional data. So this also answers kind of the second part of the question. If I have any ideas on how to improve this, not really, no. No.
Okay, maybe one intermediate solutions would be to incorporate to your segments some information coming from the 3D. For instance, I think, if I understood correctly, you consider all segments as basically the same weights, whereas maybe some are more important than others. So is it something that could be incorporated in your algorithm?
Yeah. So yeah, for now, we essentially the fidelity term we use only considers the 2D length of the segment. The length of the segment will determine how the line is allowed to move. If it's a very long segment, the line will not have a lot of freedom to rotate, for instance. It can only translate slightly. And when it's a very small segment, then it can have more freedom in the rotation. Maybe what we could do is if we could kind of gather the set of points that are associated with an edge. For instance, if we have a facade, we could give another weight to the edge from this facade, because depending on the number of points that were detected on this facade, we could weight the fidelity term using those 3D points on the facade. Other than that,
Okay, thanks. I have one more question on this part. So all along this 2D partitioning and simplifications, you are speaking in terms of infinite lines, whereas as input, you actually have finite segments. And so I was a bit puzzled about that, because for instance, for the fidelity term, you start by considering how to measure the distance between two infinite lines. And at the end, you actually do some things in between, where you consider one segment and one infinite lines. And what about directly measuring the distance between two segments? Because this is actually what you have at hand. So could you comment a bit on this?
I'm not sure I understood the question. Are you asking why we didn't use immediately the segments of the finite representation, and instead that we use the infinite one? Is that the question?
Yes, that's my question. For instance, if you have when you compare an infinite lines and a finite segment, well, actually, they can move along without changing the error. Whereas if you consider two segments, the distance might change. And yeah, I was a bit puzzled by that, but maybe I don't know, there are some practical reasons for that.
Yeah, so when we have this infinite line representation, indeed the line can translate basically along the segment. The segment doesn't move its initial information, but the cost of the line in our optimization, the cost of translating this line is 0 along the basically the line supported by this edge. Actually, this doesn't actually create any problem in the optimization. using this because this translation is there might be a slight movement of the line along this direction, but once we normalize it, we basically get the same representation. The movement of the line is perpendicular to the I think the way we express it doesn't allow for the line to move along the by translation along the direction of the segment. That makes sense.
Okay. Let's move on to the second method. I have plenty of questions. I will focus on one or two. Yes, about sparsity. Actually, it seems to me that, well, one strong advantage of your lexicographic reconstructions ID to me is that it is naturally robust to outliers. But on the other hand, it seems to me that it strongly pushes towards as dense as possible meshes as output. And as you say, for urban reconstruction, for instance, but in other applications, we are also interested in sparse outputs, especially if in case of flat area, it would be nice to be able to directly output some large triangles. And so at the end of your manuscript, to tackle this problem, you are suggesting to use some regular triangulations instead of diagonal triangulations. Yeah, since this lexicographic ordering is really strongly pushing towards as dense as possible outputs, do you think these two objectives could really be combined together?
So what was discussed at the end of the thesis is to use weights on the regular triangulation to modify the simple show complex in which we do the optimization. And in the case you described, if we could find the right weights on the set of points, so that the only triangle that there is in this complex is a very large triangle that represents the surface, we could hope that the optimal lexicographic chain uses this very long triangle. But yeah, I agree that it seems a bit contradictory to try to construct sparse representations when the lexicographic order is actually going through very dense parts, and therefore it uses a lot of small triangles. I'm not sure we would be able to combine the two.
Okay, so in order to go to allow some kind of sparsity, do you think it will be possible to introduce thresholds on your metric, so that at some point in the lexicographic order, they have all the same value, and so the lexicographic order will naturally pick solutions that are as sparse as possible? I don't know if I'm clear.
Yeah, I think what you're saying is if we could basically modify slightly this order so that triangles that would normally be very expensive, we would set the value, or we would set its order to be less expensive. Is that,
yes, at some points you don't have a total order, so they are all the same because they are all very small. Is this something possible?
Yes, it would be interesting to try. Yes, maybe yeah. In the case we're trying to reconstruct something sparse, maybe you can say at some point all those triangles, if you use it, it's all the same, and maybe that could be a yeah. But the problem is lexicographic orders are basically you can have one triangle that is slightly larger and the solution is completely different, right? It's very different from L1 or L2 minimization. So maybe the behavior would be quite unpredictable if we started to change the order.
Great, thanks. And that's okay for me.
Okay, thank you. So I guess that the advisors will ask technical questions. So maybe I will ask 2 questions. The first one is related to, say, robustness. I'm talking about the second part. Yes. Thesis. So if I understand correctly, you use floating point arithmetic to do your sorting, and so is it really? And on the other side, you have some genericity conditions. So is it really robust? Can you prove that? Well, given some errors in the computations, for example, you still get the right triangulation, Delaunay triangulation?
I think it's so. What is nice is the fact we are sure to get a result, right? Some approaches to compute the Delaunay triangulation, for instance, if you don't use exact predicates, you might not. The algorithm might behave completely different.
Yes, but what is the result? Is it a triangulation in any case?
No. It might be a very slight error in the floating point decision, which leads to not having exactly the Delaunay triangulation. But this would happen basically, for cyclic points or so, things like that, where the decision between a configuration and the flip would be very close, right? So maybe it could be acceptable to have like wait. I think it's maybe for the 2-dimensional triangulation we would still get a triangulation.
Yes, but in 3 dimensions, for example, I guess that you will, if you have slivers, you may be in trouble.
Yes. Yeah, true. Yeah, if you possibly you can get in trouble. Yeah, you cannot get a triangulation.
Okay, so there is a second side to my question. So I guess that your results can possibly be extended to higher dimensional manifold. I mean, if you can guarantee that you're at least, if you can guarantee some stability on your triangulation, if you are free of slivers, maybe you can extend your method. So the question is, can you at the same time get the triangulation, the Delaunay triangulation by minimizing these chains, but also get some triangulation which is stable? And in fact, I have in mind, maybe this is, you already thought about it, and maybe this is just a kind of naive observation, but David and others had this paper about optimal Delaunay triangulation, where you, at the same time, using some kind of minimization of energy, perturb the points so that the Delaunay triangulation is kind of sliver-free. So I was, when reading your thesis, I was wondering whether it could be possible to merge the 2 techniques to get a triangulation that is stable, which in that case I possibly could be used for higher dimensional manifolds.
So the idea would be to use the
combine, say, perturbation of the points
to ensure that
the triangulation in the end is more, say, stable.
And so when we use the minimization, lexicographic minimization, we could guarantee that it's triangulated. Right? Yes, that would be really interesting.
Okay, maybe this is some question for future. So, yes, the other question is the same nature of what someone asked. I found it a bit frustrating that your thesis contains many beautiful results, theoretical results, and also practical results. But the guarantees on the reconstructions are pretty weak. So you mentioned this paper, which is not even mentioned in your thesis, with very strict conditions to get triangulation. But I was wondering whether you can at least, well, you can find some maybe less rigorous guarantees, but at least something. Since your algorithm works very well in practice, can you guarantee something for in some cases? Can you guarantee that the distance between your result and the true object is not too big? Or well, I was expecting some kind of maybe weak results, but at least the gap between the theoretical guarantees and the practical efficiency is pretty large.
Yeah, I agree with that. Yeah, it would be nice to have a guarantee of the reconstruction we get.
But did you try hard on this question, or it's not that interesting in the context of urban scenes reconstruction?
I think it's an interesting. Yeah, definitely we need to look at what can we say about the reconstruction we have. For urban reconstruction, the most important piece was to get a manifold of reconstruction, and we know that we can get some non-manifold configurations when using our algorithm, but we know how to solve them, at least for now, for the closed surface reconstruction. So this was kind of maybe more important than the theoretical guarantee, was finding a way to repair the non-manifold configurations and get the manifold. But we don't have results on the let's say controlling the fidelity with the input set of points. This would be something we need to look into.
Okay, thank you. So now we will move to the advisors. So, David, start.
So, first, congratulations for the talk. I have one question. So, you use this lexicographic optimization with an order that is adapted for the application, which is surface reconstruction. But you could use other orders. So, for example, there could be a situation where you have a triangulated soft manifold or something, and a height function on it, or any function on it, and you would have an order that corresponds to this function. And now, what happens with the limit? And the triangulation gets final and final. If you take the optimal chains, do they tend to something? But what do they tend to?
I get the question. What did you try to do with the new order?
Well, you apply the minimization,
Yes.
but with a different order.
Okay.
Which is, for example, sort the simplices depending on what the largest value of the function on it. You suppose you have a given function.
You have a given function, yeah. Okay.
And so if you take non-zero word plus, you will get some result.
That might not be the principle.
But
would it be?
Yeah. So
and then you apply it again on this type of.
I don't know. I'm just wondering if it. I feel it will be related to the Morse complex of maybe some part of like a gradient lines or a watershed. And I don't know if you take a very fine triangulation, finer and finer, does the minimal chain converge to something that would be the minimal in the smooth, in the continuous limit, which I don't know what it is. Okay, I'm just randomly talking. I don't know. So is it a question? Yes. Random question.
Yeah, probably a good idea. I don't know. On the spot, I'm not sure.
This is a question for tomorrow.
Yeah.
So next on my list is Laurent.
So thank you for your presentation. I'd like to say that I appreciated working with you, and especially the fact you were taking care of methodology, implementation, and application, all the three together. And it's not an easy task to try to combine that, design a nice methodology, efficient implementation. We're caring about scalability, time, performance, and also you were working on real world data, quite challenging. So altogether, it's really nice, and I appreciate the fact you were not ignoring one of the three aspects, but really, yeah. I was wondering about the simplification of the 2D partition. You mentioned your perspective or possibility of future work, the fact you could adapt that to 3D partition or partition of polyhedra. So can you elaborate a bit on that? What would be the equivalent of the line in 3D?
So the equivalent of the lines would be the plates in the 3D. In the 3D method, you could we would have to change the fidelity term right now linked to the segments. If you want to use same approach as 3D, yeah, have to define also a distance between planes. It's not easy. I think the regularity term might be very similar. You could maybe take determinants of 3 plane coordinates and also compute the determinant. This would probably also be a simplification step. But yeah, the main challenge would be to define the fidelity, I think, for those planes.
And also maybe finding a nice way to accelerate the algorithm in terms of implementation.
Yes,
because I think the complexity
would have a lot more, of course, a lot more planes. But the fact we're using gradient descent, it's easy, very easy algorithm, and we could in practice parallelize the computation. So I think there are some ideas we went this way to optimize the time it takes to do it completely polyhedral arrangements.
Okay, thank you.
Thank you. So Guillaume, I forgot to ask you to ask questions. Sorry, before the advisors. So
no problem.
Yeah, if you want to ask questions. So.
Yeah. Thanks a lot for your work and presentation, Julien. So I have a question around the reconstruction with a lexicographic measure of closed surface. As you stressed out, sometimes we have point clouds that are quite sparse in some areas. And the lexicographic measure, as far as I understand it, offer several ways so that we can guide the reconstruction process. We can play with interior and exterior points, or we can play with the weights of the points in the regular Delaunay, or we could modify the position of the points before doing the Delaunay. I was wondering if you see any other way to help the surface reconstruction process. And also, I was wondering if the sharp feature estimation from your perspective could be good enough to guide the reconstruction, for example, for very thin geometries using the weights of the regular Delaunay.
So for the first question, I think the most promising way of improving the Delaunay, the results are by choosing correctly the interior and exterior constraints, let's say. The idea of the weighted points is interesting. I'm not sure what it would give, but in case where the set of points where there's a basically missing information in the set of points, I think both of those approaches might not be enough, and I don't really see a way of improving the results when there's actual holes in the set of points. For the second part, whether the critical basis and its application could be useful for thin structures, I think it could be interesting if you have something that is very thin. You can maybe hope to get from the edge detection some boundary of this area, and maybe you would not get a let's say water size representation of this thin structure, but at least you would get one part, right? Instead of having the two surfaces, would only have one that represents this this sharp feature. So maybe this is still an interesting approach.
Okay, thanks.
Thank you. So, Pierre, you have questions?
Yes. Kind of lazy. So I'm using now the camera from the laptop. So first, I want to thank you very much for a very enjoyable time during your thesis. Unfortunately, we have been shot by this pandemic. So we wish to have, we wanted to have you much more often in our lab, because we had many brainstorming sessions. And so thank you very much. I think for still a fascinating topic that has been a long-lasting problem that you can see. I believe that you show that there is still some very good ideas to push forward. So I was also like Florent, I really, I think it also was a very good contribution to have tackled both the theory, the ideas, and also implementation of application that I think will be used by data system. Very good. Yes, so I have just a philosophical question. You saw that in your cases, you have one part where you tackle like continuous optimization. The second part is also an optimization, but in the combinatorial space, right? So now, of course, it is tempting to say that in the second part of your thesis, once you have performed one optimization, you have only one hypothesis, right? That's it, for the given set of points and so on. So that should inform you on what to do to consolidate your data. So how do you see an approach in which you would iteratively use this optimization? That inform you of just one hypothesis. So now that
so we, for instance, for the so we might, from the set of points, we might run one of the lexicographic optimal algorithms, get a result, and then there's many different ways of how we can improve, right, this surface. We could try kind of like in the first work, we could try detecting planes. We could, if we wanted to then reiterate and run again the lexicographic minimum, one idea would be to move the points in the 3D space to regularize. For instance, if you have things that are close to the plane, you could move those set of points very close to the plane. And maybe this, the fact that you ran the first time you ran the lexicographic optimal, it might give you an idea of where this surface is going, and so it could be an interesting approach to use this thing to guide then simplifications, yes, by detecting in this surface planes and regularities.
Okay. So I have another slide, another question also along the line. So this, what about also the piecewise smooth variant of that? Going towards something really not just piecewise smooth, but really piecewise curve completely. Really piecewise smooth. In the sense also higher order, like curve.
Yes. But still using, let's say, the combinatorial approach of lexicographic orders, right?
Yes.
If we wanted, we might subdivide, use the first. We might use the first triangulation to resample points, and then in this resampling have smoother priors, things like that, so that the second set of points that we have is a lot more smooth, if that's the kind of criteria we're looking for. That could be an interesting idea. Try and see if we can improve the quality of the reconstruction by adding smoothness.
Okay, well, I want to thank you one more time.
Thank you.
Okay, so thank you for the questions. Thank you for the answers. So now it's time for the committee to meet privately. So I guess. Oh, sorry. Oh, sorry. Your name is the last one.
I do not have a technical question because we worked a lot together with 3 years. I just want to say that it was a great pleasure to work with you, both for your professional qualities, a good coder. I saw your code only once, and I knew that I didn't have to do it again. Perfectly confident. Your ability in other abstract mathematics, we are very able to go inside and to contribute to the proof and to write very nicely the things. And also because you are always, at least when I see you, in a good mood and always optimistic, and that's is very nice as well. So it was a chance for us to have you. So congratulations.
Okay, so it would have been a pity not to listen to all these questions. So thanks. So now it's time for the committee to meet privately. So I guess we stay in this room.
Yes.
So we'll ask the audience to be outside.
And the remote committee, of course, you stay with us. I will just say to Julien that you can maybe stop the YouTube streaming.